Download this code from codegive.com, link in the description below. OK, let's dive into a detailed tutorial on hybrid fuzzing of the Linux kernel using hardware feedback loops, HFL, specifically based on the techniques and insights presented in the Ndss 2020 paper Accelerating Fuzzing Through Enhanced Feedback from Deep Kernel Instrumentation. This will be a complex and involved process, and I'll break it down into manageable sections. Disclaimer: fuzzing the Linux kernel, especially with hardware feedback loops, can be challenging and requires a good understanding of kernel internals, assembly language, and hardware virtualization. Proceed with caution, as improper configuration or execution can lead to system instability or crashes. This guide assumes you're comfortable with using the command line, have a decent understanding of C programming, and are familiar with basic Linux administration. Also, hardware feedback often requires specialized hardware, like Intel processor trace, and the right software tooling, which might be somewhat experimental. Overview of HFL hybrid fuzzing. The problem traditional fuzzing of the Linux kernel, while valuable, faces performance bottlenecks. Software-based code coverage is computationally expensive, and basic hardware breakpoints can be too coarse-grained. The solution, HFL hybrid fuzzing with hardware feedback loops, aims to overcome these bottlenecks by leveraging hardware-based tracing and debugging features. The core idea is to use hardware performance counters or tracing mechanisms, like Intel processor trace, IPT, to gather much more precise and efficient code coverage information than purely software-based methods. Key concepts. Hardware tracing, IPT. Intel processor trace records the control flow of the executing code, branches taken, returns, calls. It's significantly faster than software-based instrumentation because it happens at the hardware level. Feedback loop. The fuzzing engine uses the IPT traces to understand what parts of the kernel code have been executed by the input it generated. This information guides the fuzzer towards exploring new code paths. Hybrid approach. Combines the benefits of coverage-guided fuzzing, AFL-like or similar, with the speed and precision of hardware tracing. This allows fuzzers to explore more complex kernel code with greater efficiency. Kernel instrumentation. The kernel needs to be instrumented to provide the hardware tracer with the necessary information, example where to start and stop tracing, identifying interesting events. Fuzzer integration. The fuzzer needs to be modified to consume the hardware trace data and integrate it into its input generation strategies. 2. Setting up the environment. 1. Hardware requirements. CPU with Intel processor trace, IPT, support. Not all CPUs support IPT. You'll need a relatively recent Intel processor, typically a 6th generation or newer. Check the processor specifications to confirm IPT support. Sufficient RAM. Kernel fuzzing can be memory intensive. 16 GB or more is recommended. SSD. An SSD for the operating system and virtual machines will significantly improve performance. 2. Software requirements. Linux host system. A Linux distribution like Ubuntu, Debian, or Fedora is required. QEMU/KVM. A hypervisor is needed to run the fuzzed kernel in a virtual machine. Kernel source code. You'll need the source code for the Linux kernel you intend to fuzz. Download it from kernel.org or your distribution's repository. Fuzzing framework. You can adapt AFL, American Fuzzy Lop, or similar frameworks, like libfuzzer, to work with hardware feedback loops. You might need to modify the fuzzer source code to integrate with your IPT analysis tools. I will provide example code based on AFL-like interface, but implementation needs to be adopted. Intel processor trace tools. You'll need tools to collect, decode, and analyze IPT data. Examples include *perf. The Linux perf tool can be used for basic IPT collection. Intel processor trace decoder, IPTD, Intel's own decoder, available from their open source repositories, provides advanced features. Custom tools. A custom tool might be required for optimal integration. 3. Setting up QEMU/KVM *. Install QEMU/KVM and the necessary packages. Make sure your user is in the KVM group. 4. Obtaining kernel source code *. 3. Instrumenting the kernel for HFL. This is one of the most critical and complex parts of the process. We need to instrument the kernel to control IPT tracing and provide context to the fuzzer. The exact instrumentation will depend on your goals and the tools you're using. Here's a general approach. 1. Identify key code regions *. Decide which parts of the kernel you want to focus on. Common areas include *system call handlers, *device drivers, especially network, storage, and graphics drivers, *file system code, *networking stack. 2. Instrumentation points *. Insert trace points or hooks at the start and end of these regions. These points will trigger the start and stop of IPT tracing. You might also want to add trace points within these regions to identify specific events or states. 3. Implementing trace points *. Using trace_print k, *. This is the simplest approach for basic instrumentation. However, it's not ideal for high-performance tracing due to its overhead. Using kernel probes, K-probes. K-probes allow you to insert code at arbitrary locations in the kernel without recompiling. However, they can also have performance implications. Adding custom trace points. Best performance. For optimal performance, you'll want to add custom trace points using the trace_event macro. This is the recommended approach for production-level kernel tracing. Let's focus on using trace_event as this will give us the best performance. Create a trace point header file. Create a header file. Example includes /trace/event/my_tracepoints.h, with your trace point definitions. Modify config. Add an entry to config, usually in kernel/config or a relevant subdirectory, to enable your trace points. Modify makefile. Add your trace point header file to the makefile, usually in kernel/makefile or a relevant subdirectory. Insert trace points in the kernel code. Now, insert the trace points into the kernel code you want to monitor. For example, to trace the entry and exit of a function. For control IPT tracing *, you'll need code to enable and disable IPT tracing based on the trace points. This usually involves interacting with the perf_event_open system call with specific configurations for IPT. Kernel module for IPT control. Create a kernel module that can start and stop IPT tracing. This module will open a perf_event using perf_event_open configured for IPT. Use ioctl to enable and disable the tracing. Potentially allocate a buffer in kernel memory to hold the trace data, or use a ring buffer. Export an interface, example via character device, for user space to control the tracing. Example kernel module snippet, illustrative. User space control. Create a user space program to interact with the kernel module. This program will use IOCTL calls to start and stop IPT tracing based on events triggered by the fuzzer. Example user space snippet, illustrative. 5. Kernel compilation * configure, compile, and install the instrumented kernel. Reboot your system to boot into the newly compiled kernel. 4. Integrating HFL into the fuzzer. 1. Fuzzer selection * choose a fuzzer that's suitable for kernel fuzzing. AFL, libfuzzer, or syscaller are common choices. 2. Fuzzer modification * the fuzzer needs to be modified to control IPT * the fuzzer needs to interact with the user space program, created in the instrumentation step, to start and stop IPT tracing at appropriate times, example before and after executing a potentially interesting input. Collect IPT data * the fuzzer needs to collect the IPT trace data from the kernel, either directly from a buffer or via a file. Decode IPT data * the fuzzer needs to decode the IPT trace data to reconstruct the control flow path. This usually involves using a tool like Intel's IPTD. Analyze the control flow * the fuzzer needs to analyze the control flow path to identify new code coverage, branches taken, and other interesting events. Update fuzzer's input generation * the fuzzer uses the coverage information to guide the generation of new inputs. If a particular input leads to new code coverage, the fuzzer will likely mutate that input further. 3. AFL-like fuzzer example, illustrative. I will provide pseudocode for integrating IPT into a AFL-like fuzzer. Keep in mind, this is a simplified example. Actual integration will be significantly more complex and depend heavily on your specific setup. Explanation **** execute _test _case, ***. This function starts IPT tracing using the kernel module, executes the generated test case, simulating a system call or driver interaction, and stops IPT tracing. Analyze _ipt _trace, ***. This function reads the IPT trace data from perf script output, and extracts the addresses of the executed code. It updates a coverage bitmap to indicate which code regions were covered. Main, the main loop generates inputs, executes them, analyzes the IPT trace, and updates the fuzzer's input generation strategy based on the coverage information. 4 important considerations ***. IPT configuration ***. The perf _event _address settings in the kernel module, especially pe.config, are crucial. You need to configure IPT to capture the desired information, example branch addresses, instruction pointers. Refer to the Intel Software Developer Manual for details. IPT data decoding ** Intel's IPTD can be used for decoding, but you might need to integrate it into your fuzzer's code or use it as a separate process. Trace buffer management * Managing the trace buffer in the kernel is important. You might need to use a ring buffer to avoid overflowing the buffer during long traces. Performance optimization * Kernel tracing can have a significant impact on performance. Minimize the amount of code being traced and optimize the IPT configuration. Fuzzing and analysis. 1. Running the fuzzer * Start your modified fuzzer. Monitor its progress. It should start exploring different code paths in the kernel. 2. Crash analysis * If the fuzzer finds a crash, analyze the crash dump, example using kdump or crash, to determine the cause of the crash. 3. Refinement * Iterate on your fuzzing setup. Refine the instrumentation, adjust the fuzzer's parameters, and focus on areas of the kernel that are most likely to contain vulnerabilities. 6. Challenges and considerations. Asterisk complexity asterisk implementing HFL hybrid fuzzing is complex and requires a significant investment of time and effort. Asterisk hardware dependency asterisk IPT requires specific hardware. Asterisk performance overhead asterisk kernel tracing can impact performance. Asterisk kernel stability asterisk fuzzing can trigger kernel bugs and crashes. Asterisk data interpretation asterisk interpreting the IPT trace data can be challenging. Asterisk tooling maturity asterisk the tooling for HFL hybrid fuzzing is still relatively immature compared to traditional fuzzing techniques. 7. Further exploration. Asterisk Ndss 2020 paper asterisk read the original Accelerating Fuzzing Through Enhanced Feedback from Deep Kernel Instrumentation paper for a deeper understanding of the techniques. Asterisk Intel Processor Trace Documentation asterisk refer to the Intel Software Developer Manual for detailed information on IPT. Asterisk Kernel Tracing Documentation asterisk explore the Linux kernel tracing documentation for information on trace_event and other tracing mechanisms. Asterisk Other fuzzing techniques asterisk consider combining HFL with other fuzzing techniques, such as directed fuzzing or symbolic execution. This is a comprehensive outline and starting point for exploring HFL hybrid fuzzing of the Linux kernel. Remember that this is a research-oriented and advanced topic, so be prepared to spend significant time learning, experimenting, and debugging. Good luck.